Hello and welcome to the Institute of Advanced Studies. I'm Ksenia Chmutina, I'm the director of the IS, and it's my absolute pleasure to welcome all of you who've joined the seminar today in the International House and online, like me. Sorry, I couldn't be in the International House in person today. And of course, it's our absolute pleasure to welcome Professor Ye Zhou, who is joining us at Loughborough today. As you probably all know, the Institute of Advanced Studies is the hub where we host international fellows who come to Loughborough University, and it's also the place that encourages and inspires different interdisciplinary presentations on all sorts of topics, ranging from current affairs to technology and science. And today's talk is the example of the latter. Just a couple of house rules. For those of you online, if you have any questions, please post the questions in the Q&A section on Zoom, and we are monitoring them. For those of you who are in the room, Kieran will help us out and take the questions. In the end of the presentation, we normally have time for questions, so please think of questions and comments. And then, of course, for those of you in person, you will have time for networking afterwards. The presentation will be recorded and will be released as a part of our video talks, but we are not recording Q&A, and also presentation will be released as a podcast. That's all with the rules. And without any further ado, I would like to invite Dr. Ye Liu to introduce our fellow today. Over to you. Thank you.
Thank you. So thank you all for joining us today in person and online. It's my privilege to introduce our speaker, Professor Ye Zhou. So a little bit introduction on the background and a little bit things. Yes, it serves as a distinguished professor at the Institution for Advanced Studies, Shenzhen University in China. He received his PhD from City University of Hong Kong, and he's at the leading edge of nanotechnology, where he specialized in nanomaterials and nanoscale devices designed for applications in neuromorphic electronics. Ye holds 25 granted patents in the US and in China. His publication record includes over 20 papers in top journals such as Science, Chemical Reviews, and Nature Electronics. In addition to his research, Professor Zhou is a dedicated member of several editorial and advisory boards, including Materials Horizons, IEEE Access. So today, Professor Zhou will share the insights from his latest research on tactile sensing devices, exploring their potentials to revolutionize how we interact with technology. So we are very honored to have him with us today to share his research and work. Please join me to give a warm welcome to Professor Ye Zhou. Thank you very much.
So thanks very much for Ye's introduction, and also it's my pleasure to be here for this great university, and thanks all for the arrangement of Loughborough University. So I'm Ye Zhou from Shenzhen University. Before my talk, I think most of you may be not familiar with Shenzhen University. So I just add 3 to 4 slides to let you know more about our university. Actually, here is 6 pictures, and you can see the top 3 pictures is actually took from around 40 years before. As you can see, at that time, Shenzhen was a very small county, and then, as you can see at the bottom of these 3 pictures, out here, we have now Shenzhen actually is a very big city in mainland China. Usually we say in mainland China, we have four leading cities, including Beijing, Shanghai, Guangzhou, and Shenzhen. So our university actually is located in the center of Shenzhen. And usually we say that Shenzhen University is the only university that has grown alongside Shenzhen since Shenzhen actually we start the reformation for Shenzhen as a year of 1978, and then at 1983 we start the Shenzhen University. So actually last year was 40 years for our university, and as you can see here, so in this picture, here is this is our Ye Zhou campus. That is the CBD of Shenzhen. As you see in this picture, actually our campus is near the seaside, and there are many top companies actually alongside our university, including some companies, for example, the Tencent. Some of you may know that usually we communicate with each other, use WhatsApp or the Line, and in mainland China we use WeChat. So the WeChat is from the Tencent, and also a very famous company called Huawei is also from the Shenzhen. And for this building, this is a Ping An Tower. That is also a very famous company which is growing in Shenzhen. And then come to my institute. Actually, our institute is called as Institute for Advanced Study. Similarly, as here is Institute of Advanced Study. So the red circle, actually, that is a building of our institute. And for our institute, we up to now we have around 46 faculties, 46 PI in our institute. And for our institute, actually, we have the bachelor program. So that is very different from other IS, for example, in here and also in Princeton. Our institute is different since we have the undergraduate students, and also we have the master students and the doctoral students. And we are mainly focusing on the 4 traditional subjects, since our students will get one of these 4 degrees or 2 of these 4 degrees when they graduate as a bachelor degree, including the mathematics, physics, biology, and chemistry. And for our research, in our institute, based on the 4 basic program from the mathematics, physics, chemistry to biology. Mainly we have 5 focused research areas, including the microbiomics, space science, nanomaterials, synthetic biology, and data science. So my research is mainly, as Yi introduced, my research is mainly focused on the nanomaterials and nano devices for flexible electronics, including the sensors, memories, and so on. So then let's start for today's talk. So my talk is based on the tactile, the sensing device. So in the first part, I want to introduce you a little bit background on this. So as we know that for our human beings, we can sense the world. So the ancient Greek philosopher Aristotle, he summarized that actually for our human beings, we have 5 senses, including the smell, sight, touch, and taste, and hearing. So that is 5 main kinds of our human beings. And in the 17th century, the Descartes, he says that when we consider how our human beings can sense the environment, as you can see in this picture. So there is a man who is touching the open flame. So how he can feel that there is some temperature signal, or how he feels the pain, which is resulting from the flame. So Descartes says that he imagines that there may be some threads which can connect the different parts of our hands, our feet with the brain. So he just simplifies that there may be a thread which can connect. One part we can sense the signal, and then we can transmit the signal to our brain. So this is very simple. And then the scientists are trying to find the behind reason of why we can feel that. So the 2 scientists has been awarded the Nobel Prize in Medicine in 2021 because of the discovery of the two receptors. One is a temperature receptor, and the other is a touch receptor. So these two receptors actually can give us how the signal, how about the temperature, how about the pain, and how we can sense them. So this is the background of the tactile sensing for our human beings. Then let's move to how we can study from our human beings to make some smart sensors or to make some electronic sensors to help us. So let's first look at how our human beings sense these signals and transmit the signals. So when we receive the external stimuli, for example, when we receive the heat signal, when we receive the vibration signal, our skin sensory receptors, as I shown in the previous slides, these receptors, they can encode and output the neural pulses. Once we have the neural pulses, it will be processed through our neurons, but with different procedures. For example, we have the adaptation of the signal, and then we may filter, we may feed some of the unuseful signal, and some of the signal is not amplified enough, then we need to do the amplification. And also for some of these signals, we need to memory it. So we have the different functions from the adaptation, filtering, amplification, and memory. And all of them will be done by the neurons and synapse. Actually, the neurons is connected by the synapse. And finally, we can achieve the tactile recognition, or we say the tactile sensing in the cerebral cortex. So this is the way how our human beings sense the signal. So for these sensing signal receptors, mainly we have three kinds of the receptor, which is named the mechanoreceptor, thermoreceptor, and the nociceptor. So with the help of these receptors, we can feel the different change of the environments. For example, we can feel the vibration. We can feel the pressure from the loading, and even we can feel the humidity of the environment, the temperature change, and also that one is very important is our human beings can feel the pain from the outside environment. So with these development of the tactile perception, once we can make the sensors based on these electronic devices, then we can do many things. For example, these tactile sensors can be used in the human and computer interface, or sometimes we say the human-computer interaction system. And these mechanisms can be applied in the intelligent robots. That is to say, these robots, we can have different parts of the sensors, and it can behave more like a human. And also, the common use is we can use it in the health monitoring. So that is a medical application. So we will see that actually the smart sensor market size is growing. That is a very important part in the whole semiconductor markets. Okay, so that is the background of our tactile sensor. Then I will discuss with you in our lab how we can achieve these different functions, or in another word, how we can mimic the human beings to make the smart sensors. So our methodology is based on the functional materials. So what can we do in the human computer interaction and in the intelligent robots? Actually, when we want to interact with the machines, or we want to make some smart machines, we need different sensors, and also we need the different components which not only can sense the signal, but also we need to transfer the signal and memory the signal. So we start to think, how can we do? So we mainly focus on the robots, the robot hand. Also, we mainly focus on the human-computer interface to see what we can do. So we start from the functional material. Since my background is focusing on the nanomaterials, and then also with the nano devices, which can sense different signals and transfer the signals into the real electrical signal. So it will be divided into two procedures. One is the signal acquisition. How can we get the signal from the device? And the other is the signal processing. Once we get the signals, then how can we process the signal and do some filtering and do some memorization, and then these signals can be very efficiently used. So our work is mainly based on these important receptors in our human beings. And so we start from the mechanoreceptor, how we can make a device to mimic the mechanoreceptor, and how we can further enhance the property of our device to introduce a thermoreceptor. And very important work is the robot. Usually we think the robot is just the combination of the different kinds of sensors. The robot may not have the pain. So how can we give the pain signal? And how can we let the robot to sense and think like our human beings? Then it can feel the pain. So that is a nonsense action. So our work is mainly based on this. So the first one is how we can make a very high performance mechanoreceptor based devices. So our work is starting from mimicking the human beings. So as you can see in this picture, that is a real skin of our human beings. Under our skin, there is some microstructure which is called the spinosome. So whether we can study this kind of the structure and to imitate the human being's skin perception function, then maybe we can get some high performance signals. But as we know, if we have some microstructure, then we can have the wider linear response range. For example, we can make some polymer structure, and it can have a very large range response. But the problem is due to the hysteresis of the polymer, then we may have a high recovery time. So this high recovery time will lead to a very low speed of this electronic sensor. So how can we do? We can give some nanostructure, since this nanostructure can lead to the high speeds. So the high speed can give us the high frequency of the sensing property. But how to combine these two structures effectively, since at some of the environments, we need both the high speed of the sensors and also a very wide range of the response. So our strategy is we can combine the microstructure with the nanostructure. So our approach is we start from a very simple copper. So this is a copper microscale mesh structure. And then we start to grow the nanowire on this structure. So in this design, we have the microstructure to help us to get the very wide range of the sensing. Also, these very small nanowires, which is growth on this copper mesh structure, can give us a very high speed response of the electronic sensor. So as you can see, first we have the primary microsquare structure of the copper mesh, and then we use a solution method to grow the nanostructure, these nanowires. So these nanowires can be sold as a secondary nanostructure, and then we have the very efficient hierarchical micro plus the nano structure. So with this structure, then we can start to sense the pressure. So as you can see, we can have a very long range of the sensing since we have this wide range structure from the microstructure, and also due to the nanowires, which is growth on the microstructure. This response speed is also very high. You can see the response time is smaller than microsecond. Then you will see that if the response time can be 0.1 microsecond or even lower, it means our sensor can get the signals, which is around maybe 1 kilohertz or 10 kilohertz. For the music, actually for our audio music, the range is around several tens of hertz to several kilohertz. So we use this kind of sensor to feel the vibration. And then actually this is one function of the rubber hand. We can use the rubber hand to touch the different vibration sounds, and then the audience, then we can recognize the sensors. But the problem is this sensor is a real-time sensor. It cannot memory. So we only can study the signals, and finally we use the neural network to separate these signals and get some feature extraction. And finally, we can recognize the signal, although the efficiency is not so high. But this kind of the sensor can really give us a relative wide range and also a very high speed from the inorganic nanostructure. And then we also think of these sensors, which I mentioned before, actually, we can only get the signals as a real time, cannot memory. So how can we memory these signals? So the sensor actually can be combined with some memory device. So our design is once we have the sensor, we connect another memory device. So this memory device is called the memories. This is a resistive type device, but with this kind of a device can memory the signals which is transmitted through the device. So once we have this combined structure, then the environment will be changed. Since before, when we have the different pressures, we can only sense the signals. But in this combined structure, if we have the pressure, actually it can memorize the sensing, memorize the signals. As you can see in this figure, with different pressure, actually the memorized signal is different. Then the sensor and the memorist, the combined structure, can be used in different ways. For example, the rubber hand, actually, they can be used to write the different characters, or even we can have some electronic pens. They can write the characters. And for the common sensor, we can only have the duration of the stroke, but we can only have the intensity of the stroke. But for this kind of the combined structure, since our memories can memorize these states. So once we have these characters and we start to use the rubber hand or the electronics pen to write the characters, they will memorize the signal, different with the common sensors. Once we don't have the pressure, then the signal will go to zero. But in this structure, you will see that they will have the memorization of these different states. So this kind of the design can help us to memory the duration of each stroke. So compare with the common character or the letter recognition, we can have another kind of signal which can be added in this recognition system to help us to improve the accuracy of the recognition. So this accuracy will be much improved if we add a memory device with the sensor. So this is a way how we can improve the sensing accuracy. So then we find that if we give the robber hand different sensors, actually it's very hard. For one common customer times robber hand, we need different kinds of sensor. For example, the mechanical sensor, the temperature sensor, or some proximity sensor. So we start to think whether we can let the robber wear a glove. Then we make the glove sensor. That is to say, these sensors are based on the gloves, not based on the robber hand. So the sensors, actually, we start to make the different sensors on the gloves. So the gloves need these wearable electronic technicians. So we choose the fabric, the natural cotton fabric, as a foundation, as a basic material to fabricate these sensors, because these fabrics, they have the advantage of the softness, the breathability, and also it is scalable. You can see we can make very large area based on these cotton fabric. We can dope the conductive inks into the fabrics, and also we can cut to make the different shapes of the sensors, and it is biocompatible. And then the problem is before we only deal with the pressure sensor, but in the real application, we have different kinds of signals. How to distinguish it? So we should have the multifunctional sensing property for these sensors. Otherwise, this intelligent sensing system should have the separated sensor and combined together. So do we have any chance to let one multifunctional sensor to sense the different signals? The way is, we can adopt the different sensing mechanism. So we can separate them. One mechanism is to get the pressure signal. One mechanism can get the thermal signal, and one can be used to acquire the proximity signal. So we use we start from the fabrics. We use thermal sensitivity. So this conductive polymer is thermal sensitive, and then we dope with the fabric. Combined with the fabric, actually the fabric is a natural dielectric material, and then we have the sandwich structure, two conductive fabric and one dielectric fabric, and it can form a capacitance and resistance for fabric structure. So we use cotton. We start from the cotton and do the polymerization and to form the electrode. And finally, you can see the very simple sandwich structure. We can use it both as a capacitor and also the resistor. So for the pressure sensing, different with the previous one. For the previous one, we use resistor signal to get the pressure sensing. But in this work, we use a capacitance signal to get the pressure signal. So based on the different pressure, as you can see in figure A, from the original state, and then with a different loading of the pressure, you will find that the capacitance will be changed if we has a different pressures. So in this way, when we measure the capacitance from the device, the pressure signal will be got. And for the proximity, also when we have the different targets coming into too close to our sensors, then you will see that the capacitance will be influenced. So we can also get the capacitance signal to distinguish whether there's some targets coming close to our sensor. And for the thermal signal, which we want to mimic the thermal receptor in the human being's skin, we use the conductive polymer. Since once the temperature is changed, then the charge hopping in the conductive polymer will have the different the porosity will be changed. So the conductivity will be finely tuned by the temperature. Then with these three mechanisms, we can make a sensor which can recognize the multiple stimuli signal, including the once we have an object, then we can feel the object shape due to the pressure, and also we can feel the proximity position and the temperature. So then we do a simulation with this simplified structure with only I think that is a 5x5 device array, and we can sense different targets with different temperature and combined with proximity signal. So this device, why this device can have the multifunctional property is due to it can either act as a capacitor, and also it can act as a resistor due to the properties of the fabric and the fabric with the polymerization. And then we also do something with the fabric sensor. So this is a work this is just accepted when I arrived London. So 2 days before. For this work, we further developed this sensor. So the sensor is also based on the fabric, but then the thing is we can use it as an authority device. As you can see in this device, usually if we have some input signal, we usually have the shape, for example. But for our device, since the sensor actually they can sense the pressure, so they can sense the intensity. So we can give the intensity also into the system. That is to say, for this encryption system, we both have the shape distinguishment and also the contrast distinguishment. So as you see in the figure at the bottom, for the first one, you can see it has the right shape and it has the right contrast. So it can pass. And for the second and third one, for the second one it has a wrong shape, and for the third one, that is very important. Although someone may have this kind of the shape, which will be memorized by him, but the contrast is wrong. So even with the right shape, we can also have the wrong identification. So here is one video which I can show you. And for the first person, you can see this is a real-time system. We have the right shape, the L, but he knows the contrast difference. But for the stranger, the wrong shape. And for the strange too, although he knows that is an L shape, but the contrast is wrong. So we can also stop him by the door. So this is just a very interesting application for our fabric sensors. And actually, these fabric sensors can be combined. With. So this is a very common drawing. We combine the fabric sensor behind this kind of the drawing. And then the most important thing I will talk is for the rubber hand. Usually we think once we give the enough sensors, for example, all these sensors together to give the rubber hand, we can sense different kinds of signal. But the problem is, how can we feel the pain? So how can the robbers feel the pain? In some special environments, we also need to protect the robbers. Our human beings can feel the pain since once we think, oh, this stimulus make me feel so painful, then I will stop to doing something. But for the robbers, in some special environments, we also need to protect it. So how can we make the robber to feel like our human beings? We need to do something. So that is a pain perception and the recognition. So usually we have several kinds of the methods to make the nonsusceptor device. So the nonsusceptor device can let the robber to feel the pain. But the problem is most of the device, they rely on the external power sources. We need to use the batteries to drive these devices, but this is not so powerful for the device miniaturization. And also some of the devices, they may have a very high power consumption. So we are thinking how we can reduce the power consumption. So we try to use the generator, that is nano generator, which is called the TNG, since it is self-powered, and also if it is used as a pressure sensor or tactile sensor, it can have the high sensitivity. And also this kind of device, you will see that it's similar with the sandwich structure, so it can be simplified, and the preparation procedure is also very simple. So we start from the TNG. So in this, in the figure in my left hand, so this is a TNG tactile sensor. And then the key problem is whether we can make the TNG system as a nonsusceptor. So we need to add another kind of the device to be connected with the TNG. So you will see that with the TNG here, and this is a rectifier. And finally, we need to find the device which is called the threshold switching device. This is also a type of the memories, as I shown before, for the rubber hand, for the electronic pen. When we need to memorize the signal, we need to connect the memories with the sensor. But here, we connect the memories with the TNG. So the TNG is the power, this is the power generator, and then the memories, we call this a threshold switching device, which can translate the signal. So the story starts from whether we have the pain. The pain comes from the pressure. If the pressure is too large with a high intensity, actually that is a pain signal. So once we have the high pressure, then the TNG will transfer the high pressure into the signal input. And this voltage applied on the memories, on the threshold switching device, will drive these silver. Actually, here is 2 electrodes, and both made of the silver, and the silver ions will be driven under the electric field, and then it will form some conductive filaments in the planar structure of the threshold device. And finally, once the silver ion is driven, and then it can form the threshold switching performance, and we can recognize the pin. So let's have a look whether we can perceive that. So this system, as you see, we make the threshold switching device, and the device variation is also very good, which can be compatible with a TNG device. So for the pain, actually, we know that we have the normal pain, but for the normal pain, we have the threshold. Once the intensity of the signal reaches the threshold, then we feel the pain. So this is a normal pain threshold. So that is for the human beings. And for our electronic device, our aim is to whether we can mimic these kinds of the pain property with the electronic device. So start from the threshold. We need to imitate how we can form a threshold. So as you can see in the picture in the figure in my right hand, you can see here is a threshold property, So start from here, the force is just 1 Newton. When the force reaches 1.5 Newton, you can see it has exceeds this threshold. So once it exceeds the threshold, you will see the output, which is located in these peaks in the red curves. You will see here is some output. So this is just the threshold property of the Nancy actor. And then also a very important property is called the hypergesia. So that means once we have the continuous the pressure on this kind of the Nancy actor, then the intensity. So this curve will be moved. So this causes the injury. Once we have the injury, we should stop. We stop the robot. So we use this kind of the device to mimic the hypergesia. You can see once we have the continuing signal input, the pressure input, then even a very small, relative small pressure can also induce the pulse outputs. Compared with this one, you can see here, we also have the output compared with the previous one. The force is also 1.5 Newton, but this is a property of the hypergesia for the pain. And also, if we have a very long time to relax, actually the Nancy actor will have the relaxation property. So then for the relaxation, we will find that once we have a certain time for our electronic device, we have several minutes, then you will see that the peak will disappear even with the same pulse, go back to the second situation. So this is a way we use the electronic device to mimic whether we can let the robot to have the pain perception and also the recognition. Okay, so this is some stories I want to share with you for our smart sensors based on the functional materials. And then for the third part, I want to give some perspective for the intelligent sensing. But actually, in these works, I have talked about all these, whether we can perceive the different signals, and then we add further functions into the system. For example, I have introduced to you, we connect the memories with the sensor, and then we can have the memory function. And if we use a neural network to analyze these signals, we can have the learning and judgment, or even we can have the reasoning function. So the development trend of the intelligent sensing maybe further go to the intelligent cognition. If we have very strong machine, if we have very strong intelligent system, maybe one day we can have the intelligent cognition. And all these functions actually need to combine the perception and memory and computation together. But the problem is for our common system, for our traditional system, the processors and the memory code, they are separated, as you can see in this figure. So this figure is drawn by my students, and we published in 2020 in a chemical review paper. So in today's human life, in the age of the Internet of Things and big data age, we have so many information, so many data coming from the sensors or coming from other places. And for our memory system, it seems our memory system is big, but the problem is we have the bandwidth limited bus. So that is called the von Neumann bottleneck. So how can we address it? We need to combine them together. So whether we can do the memorization function in the sensor, or we combine the sensor with the memory system. So then in last year, we also proposed this kind of the structure for the different 5 kinds of the sensing properties of the human beings, start from the sight and then the tactile and other smell, whether we can combine them together. The sensors combined with the memory and also the computing system together, then we can have some more efficient system to recognize the sensing signals. And all of these actually we should start from the material. That is why my group is focused on the material, especially the nanomaterial. We need to make the nanostructures and combine with some flexible substrates and some polymers together to develop the structure. So here we should start. The only way I think is we still need to study from our human beings. Our human beings start from the molecule to cell, and then we form the biological system. And for our electronic system, we also need to start from the different kinds of nanomaterial and use these materials to form the devices, including the sensors and memories and so on. And finally, whether we can form the artificial system to let the robots behave more like the human beings. So that is the goal of our research. Okay, so this is the end of my talk. I really appreciate for all your attending. And if you have any questions, we can discuss. Thank you very much.